All right, let's see what we are going to talk about. We're going to talk about molecular geometry and bonding theories. We start talking about bonding theories when we are talking about Lewis-Dot structure. So now, from Lewis-Dot structure, we can determine the electron arrangement. All right, we can see whether we have a single bond, double bond, triple bond. We can see if we have lone pair on certain atom. So that's why I say from Lewis-Dot structure, you only determine this information. Now, combining this information with the new theory, which is what VSEPR, we can determine the shape and geometry of the molecule. Now, when we are looking at the shape, all right, the focus is on the shape. We're only looking at bonded atoms. In any of these cases, you don't see any lone pair, even though you have to have a lone pair, all right, for this to be bent. Because according to the VSEPR theory is a valence electron pair repulsion, is a repulsion among electron groups. And what we say electron groups, so in your textbook, it called that electron domain. So what we mean basically, we mean that, let me just put it here. This is a lone pair, hypothetically. There is a repulsion between the electrons, right? This is VSEPR we're talking about, repulsion between electrons. And it doesn't matter whether these electrons, they are bonding electrons, because this bond is made of two electrons, or they are non-bonding and is a two, like two electrons come together, we call them a lone pair, all right? And then again, it doesn't matter whether these electrons, they are what? Double bonded or triple bonded. It doesn't matter. You see, in case of CO2, this is a, this is a Lewis-Dot structure of CO2, remember? So looking at the carbon center here, you will see that there are two electron groups on each side. Two electron groups on each side. Here in this case is a double bond, all right? But remember, even the double bond count as one single electron groups. So this has two electron groups here in this case. Okay, we'll get into that later on. Now, as far as the angle goes, angle is very easy because most of the angle, they are really logical, how you determine the angle. The only angle that is a little bit you need to pay attention is what? Tetrahedral angle, and that is 109.5. Now, to understand the repulsion between two electron groups, you know, obviously, if we say this is a person, and this is a person, and this is a person, these two persons want to be away from each other, the furthest they can get would be 180 degrees. And 180 degrees is very easy to see and detect. In case of trigonal planar, if there are three people want to be away from each other the furthest possible, so the only possible way to would be 120 degrees, because the whole circle is 360. Half of it would be 180 divided by 3, it would be 120, all right? Now, in case of trigonal bipyramidal, remember this is the triangle, all right? The triangle sitting here, and this is go through the axis right there. So if this is the triangle, the angle would be like similar to this, would be 120, And the relationship, since this is exactly perpendicular to the triangle, would be 90 degrees. In case of octahedral, you are exactly sitting in the top of the square right there. It's a perfect square and is axial going through it. So everything is 90 degrees with respect to each other, because if it's a perfect square, it's a square right here, you can see that these relationships, they're all what? 90 degrees. Okay. So back to electron group or electron domain, as your textbook says. Remember, these bond made of 2 electrons, and they repel each other. And for 3 electron group, you expect to have a trigonal planar, all right? And the angle to be about 120 degrees. So then again, we're going to define electron groups. You look at, I want you to tell me how many electron group you see around this B here. How many electron group do you see? Come on, guys. You can answer that.
3.
All right, let me count it with you. This is 1. This is 2. This is 3. This is 4. So for electron group, it could be lone pair, single bond, double bond, triple bond. So here we can have lone pair, yes. For this one, single bond, double bond, triple bond. Each one of these count 1 electron group. Now, I'm going to ask you a question. How many electron group you have for this one?
3.
Everybody see that?
4.
Yes.
Somebody says 4. Okay. Let's see. This is 1 electron group. This is the second electron group. The whole double bond count as what? 1 electron group. So that is 3 electron groups. So for central A, how many electron group do you see, folks?
4.
Everybody see that? Does anybody don't see? So we count it together, just make sure. This is 1 electron group because lone pair, single bond 2, double bond 3, and this is 4. Okay, good. So we understand electron groups or electron domain, they're same thing, right? All right, so regardless, single, double, triple. Now let's look at here. Oxygen, give me the electron groups, guys. This oxygen.
3.
3.
Agree? All right, how about nitrogen?
3.
3.
How about this oxygen?
4.
Very good, very good. You see, this is so important to understand electron groups, because when we come to the geometry, then, all right, you will see these informations are important to determining the what? Geometry. Now, as you see, it says you have like 3 lone pairs right there. 1 single bond, talking about this oxygen, right? And 1 double bond. So again, this chapter emphasis on VSEPR. VSEPR is valence shell electron pair repulsion theory. And as I mentioned, it's very simple. These electron groups try to get away from each other as much as possible. So the repulsive forces is making geometry arrangement, basically. All right. And on basis of this theory plus Lewis, all right, we can determine what? the geometry and the shape of molecule. All right. You see, in the case of carbon tetrachloride, we have how many electron group? 4 electron group. So 4 electron group, it gives us what? Tetrahedral structure. 1, 2, 3, 4. If you look at what I'm doing, I am not counting the atoms here. You see, I'm focusing on electron group. Electron group definition is either single bond, double bond, triple bond, or lone pair. That's it. So don't get that confused. All right. Now, obviously, with Lewis structure, we get electron arrangement. Then we have to use VSEPR to determine what 3D model or the shape. So what are the bond angle? We briefly went over this, and we're going to do it again. What do the shapes of the molecule depends on? What is its shapes? These shapes depends on what? What constitute a group? All right, we're talking about electron group. We understand that. Are all the groups treated the same? We just said lone pair, single bond, double bond, triple bond. Can we say all of them are exactly the same? No, obviously not. Because lone pair, all right, electron has more dispersion, right? Because they're not confined between 2 nucleus. When you have a bond in between A and B, these electron confined here. All right, more confined. Whereas when you have a lone pair, the electron are what? Just left alone and takes much more volume. In that sense, we can say that, make a difference. Obviously, single bond, double bond, triple bond also is different. This takes more volume than this one. 3 takes more than 2. Okay. Okay, now there are a couple of terminology here. Let's clarify that. Electron group geometry or electron domain geometry, and then we have sometimes called orbital geometry. Technically, anything related to electron and word geometry is purely talking about what? Electron groups. You got what I'm saying? So somebody asks you, what's the electron geometry or electron orbital geometry or orbital geometry? Because it's an orbital, you understand, orbit is made of what? Electrons. So orbit electron geometry, this talking about what? Electron groups. An electron group can be a lone pair, double pair, remember? We just said that. Now shape, you only looking at bonded atom. For that shape, or what we call it, molecular geometry, this is shape. This is shape, basically. So you're looking at the shape. Let me give you an example to understand. This. What is this, guys?
The H2O, is that what you're asking?
Exactly. It's water, right?
Yeah.
All right. So being a water, we look at the central atom, oxygen. I'm going to ask you a simple question. How many electron group with oxygen you have?
4.
4. If you have 4, the only structure possible for this, or only arrangement possible, would be what? Tetrahedra. You got what I'm saying? Now, somebody asks you, what is the electron geometry or orbital geometry of water? The water is tetrahedral. But the shape of the water is this. This is the shape of the water. And that suggests true. These are sitting here in the form of tetrahedral. Let me put the electron here so you can see it clearly. These are two lone pair. These lone pair, but the shape of water is what? This here bent. Because when we're talking about the molecular geometry or shape, we are mainly focused on what? Bonded atom. You got what I'm saying? Okay. All right, let's go through all these things one by one, because we should understand what are the 2, 3, 4, 5, 6 electron group. We're going to be looking at the electron groups and its derivative, which means, derivative of this, because you could have here bonded atom, or one of these could be lone pair. Same thing for here. You could have something here with the lone pair, and that with the lone pair, when we say a lone pair, that means this is sitting here, and this can be bonded to something else. This is still 3 electron group. And then you could have also this, right? There is a difference between these two, because for this one, all right, electron group is 3, right? 3 electron group you have. And then what is happening, all of them are bonded. If they are bonded, all right, if they are bonded, then we say this is AX3. Therefore, this would be what? Trigonal planar. Trigonal planar, right? Now, in this case, still 3 electron groups. As far as the electron geometry goes, still is trigonal planar, all right? But shape is what? Shape is what? Bent. Whereas here, both shape and what? Electron group, they're all trigonal planar. So you see the difference, right? So let's look at each one. 2, you have 2 here. Example is given to you. What looks like linear, right? And then you have 3. And you see it's 120. This is trigonal planar. Now you have a derivative also of each one of them that we're going to go through it later on. 4, that would be what? Tetrahedral, example. 5, trigonal bipyramidal. You see, this is a triangle sitting here. You see this triangle? You see this triangle? There's a triangle and 2 pyramid on the top. So that's what we call it, trigonal bipyramidal. Octahedral actually was a square bipyramidal. That's an old name. Then later on, it changed it with octahedral. That means 8. Octa means 8. 8 faces here. As you see, these are the electron group, 2, 3, and then you have 4, 5, 6. 2, 3, 4, 5, 6. And these are all of them. You see the difference between electron, domain geometry, or simply orbital geometry, or what we call it molecular geometry or shape. Okay, let's look at derivative. When you have this case that you have linear, all right, you could have this double bond and it still would be linear, doesn't matter. Some example. All right. Now, this is the 3 electron groups. As you see, these are all bonded atom. Therefore, both geometry both electron geometry and molecular geometry would be the same, right? For this one would be trigonal planar. However, for this one, electron geometry would be what? Trigonal planar, because it has 3 electron groups, but the shape would be what? Bent. This is another example, right? You have bonded atom, double bond. All right, you look at this one. Again, same thing here, 3 electron groups. Now you have another one. Now this is an interesting case because in this case, this is a double bond. If you look at this, having 3 electron groups, all right? Having 3 electron groups, this is 1, 2, 3. This gives you what? Trigonal planar. In the case of trigonal planar, the angle, expected angle is 120 degrees. However, when you check this angle, you see that the angle involved double bond is a little bit larger than what? 120. And the other angle, therefore, is smaller, is 111 compared to 120. So what is happening here? We say, because of the double bond here, you have more repulsion pushing these electron further away than expected 120, okay? So you have in the test, you could have question, this angle, is it 120, greater than 120, less than 120, or what, so forth? You know, this is something good. All right, let's look at this one. Now we're talking about 4 electron groups. Now, 4 electron groups, derivative, one of them can be what? Ammonia, because you see you have 1, 2, 3, 4. 4 groups you have here. That's the 4 electron groups. The electron geometry would be what? Tetrahedral. But the shape, because you don't no longer looking at this lone pair, you only look at the bonded atom. Looking at the bonded atom, this looks like a what? A pyramid sitting on top of the triangle. That's why what we call it what? Trigonal planar. Okay. So trigonal pyramidal, trigonal pyramidal. Now, trigonal pyramidal, it has 1 lone here. Now, if 2 of the electron groups, one here, all right, then you still have tetrahedral electron geometry, but shape of the molecule would be what? Bent. This is example for, this is ammonia example, and this is water example, right? And we can see this here very clearly. All right. Do you guys have any question on this? No?
No.
All right. Now, these are the summary of derivative for tetrahedral electron geometry. All right. The only thing about tetrahedral is their angle is not so visibly determined. You got to know the angle itself. And you're looking at the angles, obviously, in the case that you have 1 lone pair, 2 lone pair, this angle here, all right, you expect, because of higher dispersion, higher volume, you expect this angle to be less than what? Tetrahedral angle, which is 109.5. Now, having 2 lone pair, okay, they are further push and make this about 104 point something or 105. Okay. You don't need to memorize that, but you need to know whether the angle is greater than tetrahedral angle or same or less. Okay. Now you see the difference between an electron, bonding electrons, and the electron that is non-bonded. So in this case, lone pair has higher volume. Methane is an example of tetrahedral geometry, both electron and shape. This would be electron geometry, would be what, tetrahedral, but the molecular geometry would be what, trigonal pyramidal. Now this one is also same as the other one. You see you have 4 electron groups around AS, and then 1 lone pair, so that cause to geometry would be what, pyramidal. Yeah, trigonal pyramidal. These are pyramidal. Now, water, as you see the lone pair, 2 lone pairs, molecular geometry is bent, but electron geometry is what, tetrahedral. This is another one, tetrahedral bent shape. ClO2, right?
Yes, sir.
Yes, go ahead.
Like one slide. Yeah, right there. Thank you. I just want to see that.
Not a problem. Okay, here we have tetrahedral again, but this one has 2 lone pair. Now we reach 5 electron group. For the 5 electron group, you see the derivative is higher than the other one, all right, because you have more choices now. For trigonal bipyramidal, if you pay attention, there is something very interesting in trigonal bipyramidal. You look at this triangle, all right, the position of these bonded atom within the triangle, we call this what, equatorial, all right, equatorial. And the position that going through the triangle, this we call it axial. Now something interesting happening, because technically speaking, when we put the lone pair, we can put it anywhere we want to, right? But why is this? The lone pair sitting in this position is within the plane of what, triangle. So is in the position what, equatorial, not axial. And you see, they're all in position what, equatorial, and they're not axial. And there is a reason for that. And that reason, if you look at this, when you put the lone pair here, all right, the molecule will be more stable. Why is that more stable? Because what we are looking at, to put it somewhere with whereas we have less repulsion. Less repulsion, okay? So let's identify what type of repulsion we're talking about. Since, you know, the 90-degree is a high repulsion, let's look at the 90-degree repulsion. Okay. 90-degree repulsion. If I put the lone pair here, how many 90-degree repulsion I get? Can you guys see that?
Wait, sorry, can you repeat where the lone pair is? Is it the one on the seesaw?
Do you guys see what I'm drawing here?
Oh, right there, got it.
I said, if I put the lone pair there, all right, how many 90-degree repulsion?
3?
Exactly. You have this 90-degree here, 1 here, 2, 3 here. Now, whereas I put it here, how many 90-degree repulsion I get here? This is 3 repulsion.
Is
How
that
many?
1?
You get 1? You sure?
Yeah, I think so.
Okay.
Oh, wait, no, yeah, you could get 2 if that's going straight out.
If you actually look at it, these are all same because they are in the body of triangle, right? You see that, right? Maybe you can see easier in this one. If I put the lone pair here, all right, then I should see 1 and 2 repulsion.
Got it.
You understand what I'm saying? So since equatorial position, you have less 90-degree repulsion, this position is preferable. So to say that, you know, having a lone pair in axial position, it never happens. Okay. All right. Back to what we were saying. Now we are clear where we put the electron here. Well, we put the lone pair here, electron here. Then we see something like seesaw. You cannot see the seesaw right now. I'm going to show it to you. And then you put another lone pair. Then you see a T-shape. T-shape, you can see it here. And now you put 3. Then you will have what? A linear, right? So let's look at all these things, you know. You can read that later on. Now, axial position, equatorial position. See, remember, this is a triangle basically sitting here. All right. So you know where the axial and triangle is. Now, you're looking at the 90-degree and 120-degree angles. When we have something like that, we put the lone pair here. That's a triangle, trigonal bipyramidal. We put the lone pair here, all right? Then obviously this lone pair may make this angle to be a little bit higher than what, because there's a lone pair here, more repulsion than what one typically that you expect to have, all right? So between these two would be higher than 180, and this is less than 120, all right? So we never put the lone pair what in this position. Always he has to go in this position. This is what axial and is wrong. Okay, so the seesaw, for you to see the seesaw, if I turn it around like that, you can see the seesaw. You can see like 2 kids sitting here, similar to the seesaw you see in the park. This goes down, this goes up, go up and down, right? Like a seesaw in the park, you know. So that's the name coming from seesaw. All right. Now you got seesaw. Remember, this is a lone pair here, and this trigonal bipyramidal, and this is a Lewis-Sutter structure, basically. If you notice that the sulfur is violating, you know, octet rule in this shape, and there is no other way, it has to violate the octet rule. And we look at the sulfur being a 3rd row is acceptable. I just briefly want to mention that. Now, in the case of you having 2 lone pair, this is very easy. This is a T-shape. Remember, even T-shape for this electron geometry is still trigonal bipyramidal, but the shape, molecular geometry is what T-shape. We're going to be doing some of the practice like this in a few minutes in the class, so you guys don't have to memorize it, and I'll show you how we're going to practice on that. Okay, now you're looking at here, obviously, you see how many electron groups on chlorine, folks?
5.
Yes, it's very easy to see 5. Immediately, you see what? Trigonal bipyramidal. You got what I'm saying? Trigonal bipyramidal. You have a triangle, and then you have 2 pyramids sitting on top of the triangle. Trigonal bipyramidal. That's the electron geometry. Now, in this case, you have what? 2 of them here is electrons. So if you have 2 electron groups replacing a 2 bonded, so this is what you're going to have. Basically T-shape. Now xenon, this is very interesting, because this formula right there, somebody asked you, what's the electron geometry? Is what? Trigonal bipyramidal. And these are all lone pairs, so that makes this to be what? Shape would be linear. All right. Now we reach octahedral. Octahedral, as I explained, these are all equivalent, everything 90 degrees. So there is no axial and equatorial position, right? So you put the lone pair, put it anywhere you want to. You can turn this around, it would be the same thing. If you put the lone pair here, then you would see here square, all right? And then obviously this is the pyramid. So it would be what? Square pyramidal, right? Now, If we got two lone pair, you have to put them right here in the opposite position. Therefore, this would be just what? Square planar. Very easy, square planar. So obviously, if you eliminate one of this with another electron group, then you would have a T shape. And then we'll lose another one, then you have linear. Of course, these molecules have so many electron groups. It's not, I haven't seen such a thing, but just in case. Okay. All right. So now these are all 90 degree. You see very nice sulfur violet in octet rule there. BR again here. You see what is happening. BR is third row and below, violet in octet rule. And in this case, it has one lone pair. So that makes this what? Electron geometry still is going to be octahedral, but molecular geometry would be what? Be square, right? And it's a pyramid. So we call it what? Square pyramidal. All right. Now, if you have two lone pair right there, then you call it what? Square planar. All right. These are all the derivatives. Now, your job. Determine PCl3 bond angles and geometry. Can you do that? You got to start with drawing Lewis structure, then determining how many electron groups you have, then determining how many lone pair you have, then you come up with the structure. Can you do that? Easy. Let's see. All right. First we do the Lewis dot structure, then we determine the electron groups. To do Lewis dot structure, you count the number of valence electron. All right. Is that the Lewis structure you came up with?
Yes. For me, yes.
Yep.
Okay, this is what you came up with. That's good. All right. So you see how many electron groups you have, right?
Yep.
How many electron groups you had? 4, right? You see them? Okay.
Yep.
All right. Now, one of them is a lone pair. So that makes the geometry to be what? Trigonal pyramidal. You see that?
Mm-hmm.
And it suggests the angle to be less than 109.5 because of the lone pair. If it was bonded atom, then it would be perfect, 109.5, perfect tetrahedral angle. So that's what the shape would look like. All right. Let's do another one. I'm gonna do this one, guys. All right, let's see this one. All right. We put the silicon at the center because it's least electronegative. And then we count the valence electron, all right, total, the bonding electron, right? Because we got to draw the structure to see the bonding electron, and then, remaining electron. So this is the structure it look like. Now count the number of electron groups. You have 5 electron groups. And 0 lone pair. That would be what? This. Okay. Any question? All right. Now, I want to give you something. This is very interesting. I want you to do this one and do it yourself. And you come up with the structures, right? And tell me, we're going to talk about this more. Okay, let's just focus on one at a time. Let's do the Lewis dot structure. This is a Lewis dot structure we have. All right, is it okay with you?
Yep.
Is that what you guys come up with?
Yeah.
All right. Just be very careful. This Lewis-Dot structure is preferred according to the Lewis theory. But according to the formal charge, you could have a better resonance for this. Can you come up with the better resonance for this? Guys?
Why didn't you get a double bond somewhere?
All right, let's do it, see what you get. Where we put the double bond, then what formal charge we have? As it is, the formal charge of this one is -1, -1. What about this one? 1, 2, 3, 4, 5, 6, 7. Right? What is the formal charge of fluorine?
0.
0. What's the formal charge of chlorine?
+2.
+2. So the atom is not ion, it doesn't have any charge, so everything is okay. Now, can we come up with the better structure that minimizes the formal charge? Anybody came up with the better structures or no? You guys not doing it.
I'm clueless.
You're clueless. All right. So how can we improve the formal charge? You say this is +2, right? And this is -1. Can we this +2 make it 0?
I don't see how you could.
All right. Let's see. This is +2. This is -1. This is -1. Alternative Lewis-Dot structure. Fluorine, right? Oxygen, oxygen. I'm going to collapse this 2 lone pair here and make it double bond. All right. Do the same thing to this oxygen. This, make it double bond. All right. Now I have a lone pair here. For fluorine, I'm not touching it. Cl, by the way. So Cl is violating octet rule. Can it violate octet rule? Is it third row and below?
Sorry, what did you say after can it octet? Can it?
Can Cl violate octet rule? In order to
It
have
can if it has to, right?
Yes.
it can if you get the better, gives a better formal charge. What's the formal charge of right now of chlorine here in this case?
0.
0. What's the formal charge of oxygen?
Both of them are 0.
0, 0, 0. Now, which structure is preferred?
The right.
The one down to the right. You got what I'm saying? This is according to formal charge. This is according to the Lewis theory. Just the Lewis theory would give us this. We only find out about this one if we apply what? Formal charge theory. You got what I'm saying? All right. Now, let's see, because the question about this problem, it was not only to find out the Lewis-Dot structure, is to determine the molecular geometry. Now, looking at the molecular geometry, what's the molecular geometry? What's the electron geometry of this? Electron geometry is what? For this is what, folks? How many electron groups you have?
4.
Yes. So therefore, the electron geometry would be what? Tetrahedron. Correct? What's
Okay.
the molecular geometry or shape? What is the shape? Well, the shape, we are only look at the bonded atom. That means we don't look at what? the lone pair. How many bonded atom you have? You have 3. And having a one lone pair with 3 bonded atom, that gives us what shape, guys? Trigonal pyramidal.
Pyramidal.
Yes?
Mhm.
How about this one? Still, same thing, exactly same. And the shape, exactly same. Because you still have 1, 2, 3, even though they're double bond, you have electron group would be 1, 2, 3, 4. So that would be tetrahedron. And one of them is a lone pair, then would be what? The shape would be what? Trigonal pyramidal.
It makes sense when you do it. I just would need to practice it, I think.
Yes, that's why I'm doing it. So you will see how you go about it to try to minimize the formal charge, right? Obviously, there are more than one resonance. You know, there is another resonance here for this structure. All we have is dry, and that would be 2 double bonds, single bond, single bond. In this scenario, you will have a 0 formal charge here, all right, and +1 here and -1 here, and these would be 0. Instead of 2 double bond, you have 1 double bond here. This is better than this one, all right? But
But
this,
worse than that one.
yeah, but this is the best in terms of formal charge. Do you agree with what I'm saying?
Yeah.
Professor,
Yes, sir.
what do you recommend for like as far as the shape after you draw the structure, the geometries? Like, what's the best way to kind of memorize those?
Memorize it. I'll show it to you in a second, okay? So this is to simplify it according to just Lewis theory. This is what you're going to come up with, and we came up with that. All right. Now, if you have a larger molecule, obviously, you can just say this is tetrahedral. You have to segmentize. You need to look at different segments. You have to different part of that molecules to be able to identify. And then you look at the central atom. You see, okay, I have that many electron groups, and that's why I have this geometry for this one. For example, you see for this carbon, I have 1, 2, 3, 4 tetrahedral. All right. For this one, you can say, okay, I have 2 electron group, 3 electron group. You got to look at it each segment. Yes. Now, looking at this, all right, these 2 electrons is all belong to this oxygen here. Let's see if we can identify the electron group. How about this carbon? Electron geometry, what is it? You say, I have 1, 2, 3, 4 electron groups. So the electron geometry suggests what? Tetrahedral. You get what I'm saying?
Okay.
And molecular geometry, since they're all bonded atom, is going to be what? Tetrahedral. For that carbon, we're done. Let's go to the next carbon. How about this carbon right here? You say the electron geometry is 1, 2, 3 groups. So is what? Trigonal planar, right? Trigonal planar. What about shape? It says it's the same because it doesn't have any lone pair. So both lone pair and what geometry, shape is going to be what? Trigonal planar. Let's do for this oxygen. How many electron groups you have?
4.
4. That would be tetrahedral. Electron geometry. Shape.
Is it bent?
Bent. Very good. Now for this one, how many electron groups you have?
3.
And it would be 2 lone pair. This is linear, right? You see that? Yeah?
Yep.
Okay. Now, as I said, you need to first make sure you know the Lewis-Dot structure, because if you don't know Lewis-Dot structure, you cannot say this is bent. How would you know it's bent if then you should have 2 lone pair here to make it to the band. Because for this oxygen, you have tetrahedral electron geometry. 1, 2, 3, 4. But having 2 electrons make it to become what? Band. Let's do. Give me electron geometry of nitrogen. Electron geometry of nitrogen. How many electron group nitrogen has, folks?
4.
So that would be what? Tetrahedral,
That-
right?
Okay, yep.
Yeah. So what would be the shape now? Shape for this nitrogen? A pyramidal, that's correct. Let me pause this here because somebody asked me how we know these shapes. I'm going to go back to this slide, okay? Let's do something else. You see where I am, right?
Yeah, we could see it.
Okay, let's just play this game. Guys, this is 1 hour spending with me. I mean, it's not the full hour. This hour, you will learn everything if you pay attention. Let's look at the model. Now, in this model, what do you see? This is the central atom, right?
It's linear.
And these are terminal. So if I ask electron geometry would be linear. If I ask molecular geometry, also will be linear. Do you guys see that?
Yep.
All right. Now, if I get rid of one of the bond, put it a lone pair. So still, I will have linear, linear. You guys see that?
Yep.
Yeah.
Now, I take the lone pair, I put the bond pair. Now I want to put another bond here. So what do I have here? You said, what's the best way to learn it, right? So electron geometry would be what? Trigonal, planar, because this is a triangle, right? And then molecular geometry also would be what? Trigonal pyramid. And if I show the bond angle, you see it's 120, because 360 divided by 3, it gives you what? 120. So far, any problem?
No.
All right. Now, what if I take this, one of these bond out, take this out, and add a lone pair? Still, electron geometry would be what? Trigonal planar, because I have 3 electron groups, 1, 2, 3. But molecular geometry, or the shape would be what? Bend. An angle, this should be less than 120. Just don't get confused, all right? You guys see that? Because when we look at the molecular geometry, you don't see this lone pair. You see, I click on this, don't show lone pair. So you see bend here. So molecular geometry is where we don't see lone pair anymore. We just look at the bond pair. How are we doing?
Good. This is helpful. Thank you for posting it.
Okay, I want to get rid of this lone pair. I put one more bond pair. Or did I do this one right now? Okay, I didn't do this one. Let's take another one out and put 2 lone pair. Now, what's the electron geometry of this, guys? What's the electron
Is
geometry?
it the trigonal planar again?
Electron geometry, still you have 3 groups. One, this is a bond, lone pair, that's 3 groups. Still would be called trigonal planar. You understand that? You know, 3 electron groups,
Yes.
that would be what? Trigonal planar. Now, molecular geometry for this one would be what? Linear. Because if I click on this, don't show lone pairs, you see linear here. You see that?
Mm-hmm.
You only see bond pair. All right, now we're done with this. Let's just put, we're done 3, right? Which that's what it is. Now add another one, 4. This would be what? Tetrahedral. You see that? And the angle would be what? 109.5 tetrahedral. In case of tetrahedral, right, both these are the parent model. So molecular geometry and electron geometry would be same. Now, if
Sorry, is that because there's no lone pairs?
exactly. So molecular geometry and electron geometry would be same when there is both there are, right? No lone pair exists. Now, look, if I remove one of this bond pair and add the lone pair here, electron geometry is still tetrahedral. Do you understand why? Because we have still 4 electron groups. This is 1, 2, 3, and the lone pair can add 1, that's 4. And whenever we have 4 electron groups, it is what? Tetrahedral. Now, the molecular geometry or shape would be what? We only see this part. We don't see lone pair. So that means you see a pyramid sitting on top of the triangle. So we call it what? Trigonal pyramidal. This is a trigonal pyramidal. This is the pyramid sitting on top of the triangle. Okay? We're good? Now, let's take another out. Oops. I meant take it out. Take a bond out and put another lone pair there. Now, in this case, what do you see here? Electron geometry is still tetrahedral, but you see shape to be bent because when you look at the shape, you don't see the lone pair, all right? You don't see the lone pair. You just see the bond pairs, okay? Is this helping or what?
Yeah.
Definitely.
Yeah.
I take another one, put another one here. Now you see, this still tetrahedral, but literally in terms of shape, it would be what? Linear, because you only see the bond pair. Okay. Now we go to 5, 2, 3, 4, 5. 5, you see clearly a triangle. You see the triangle? This is a triangle, right? And if you draw here, then you have 2 pyramids, one on the top, the other one in the bottom. So that's why we call it trigonal, bi meaning 2 pyramidal. There are 2 pyramids, they're sitting there. Both shape and what? Electron geometry. Now, what if I take one of these bonds out, put the lone pair here? Then what do I have?
Same thing for electron.
Then in this scenario, the molecular geometry, you cannot look at the lone pair. What you see is a seesaw. Kid sitting here and one sitting here. This is going up and down, seesaw. You guys see that?
Yeah.
Mhm.
Yep.
Now, if I take another bond out, and put another lone pair instead, what do I see? What does this look like? This looks like a
T-shape.
You see that? It looks like a T-shape. But electron geometry is trigonal bipyramidal. How about if I take another bond out and put another lone pair? So what do I have here?
Linear. Yeah.
You guys see that?
Yep.
All right. Let's do 6. This is 2, 3, 4, 5, 6. This is octahedral. You see, it's a square right here, 2 pyramid. The old name used to be square bipyramidal, but we don't call that anymore. We call it octahedral. In an octahedral, everything is 90 degrees. And if you take one of these out, replace it, then you will have what looks like this square pyramidal. You see the square, guys? You see the square right there, right there? It's a square. This is square. And since it's a lone pair, you see, we always say you don't see the lone pair. So when you look at the shape, you don't see the lone pair. You can see the square, what? Pyramidal. And if you draw this here, then you get the pyramid. We're good? Now take another one out and put another lone pair, then it would be square planar. Yeah, this is a planar. It's flat because you don't see this bond. You just see a square right there. And that's a square planar. Even though those are there, still is octahedral electron geometry, but the shape or molecular geometry is square planar. How are we doing? Is it okay? Take another bond out. Take another bond out, and another lone pair. Now you see, do you see T-shape here, folks?
So, Professor, in this case, the electron stays the same, but the molecules change, right? Because there's more lone pairs.
Say the electron geometry, electron geometry stay the same, but the shape is different. You
Okay.
understand what I'm saying?
Yeah.
Because you say electrons stay the same. What do you mean
I
electrons?
meant electron geometry. I just said it.
Electron geometry, correct. All right, you take another bond out and put one more lone pair. What do you have here? Obviously, you have linear here, you see? This is a linear. And electron geometry still would be octahedral. So what do you think, guys? Do you think you learn it like that or no?
Yeah,
This-
that makes
it's not-
it really, that's helpful.
That's where we were, right? Now let's talk about stuff here. For this nitrogen, the one to the left here, the nitrogen is, what's the electron groups on nitrogen? Now you should be able to pick this up easily. Electron groups,
Four.
folks? Huh? How many?
4.
4. All right. So therefore, the electron geometry would be what? Tetrahedral.
Tetra.
Right? Tetrahedral. Okay. Now, if the electron geometry is tetrahedral, what's the shape for this nitrogen? You don't have
Trigonal,
Yeah. pyramidal.
pyramidal. Okay.
Just say pyramidal. You see, don't, if it is difficult for you, all right, don't torment yourself. It says, okay, is a pyramid sitting on top of the triangle. Think of that. You see that clearly, huh? Or no? For a tetrahedral, having
yeah.
a lone pair, then you have a triangle sitting the a pyramid sitting on the top. We call the trigonal pyramidal. All right, trigonal pyramid. Okay. Now, how about this carbon? What do we have here?
So 4 electron groups.
All right, no lone pair. So
No.
therefore, electron groups and shape, they
Same.
both tetrahedral. How about the carbon next to it? How many electron groups you have?
3.
All right. So if you have 3, all right, no lone pair, that makes it trigonal planar.
Planar. Right.
How about this oxygen? How many electron groups you have?
4.
Okay, therefore this would be what? Tetrahedral electron geometry, and molecular geometry or shape would be what?
Linear.
So you have
Would
to-
it be linear?
if you have 4 groups,
Oh, you're right.
it would be
Jared's right.
what?
It's bent.
Bent. Yeah, there you go. Yeah, it's okay. No, you can obviously see that in a 3D model, but you know, if you have a Lewis dot structure, then you have to come up with this name yourself. Okay, let's do this one. Did you guys come up with this Lewis structure?
Yes.
Good. And then, right, in terms of the geometries, that's what you should come up with. Okay. Remember, beryllium and boron, they're electron deficient, they're violation to octet root, right? They're exception to octet root. And that is the best electron arrangement for what? Boron. Any question on this? All right, let's talk about polarity. We mentioned earlier in earlier chapter that the polar bond is the one that has the higher electron negativity difference between two bonded atoms higher than 0.4. And the benchmark was what? Carbon and hydrogen, and go all the way to close to 2. That region, it would be considered polar. Anything beyond 2, it goes to the ionic bonding, right? Now, how we look at the fact that, you know, some molecules, in order to determine the polarity of that molecule, they must have at least polar bond, which means if you don't have a polar bond, the whole molecule is non-polar. So any hydrocarbon compound, I mean carbon with the hydrogen, any shape it has, it doesn't matter how large the molecule it has, would be considered to be what? Non-polar, because nature of that bond is what is defined as non-polar. Now, in order to look at the molecule itself to see whether it's polar or non-polar, then we need to take a look at the geometry, all right? Otherwise, it's going to be hard, because now you look at this versus this. Which one is polar, which one is non-polar? Huh? Can you tell me, Fulay?
The one on the left is non-polar, the right is polar.
This is polar?
No, the left one is polar.
This is polar? And this one is what? Non-polar? Is that what you're saying?
Yeah, sorry, I mixed them up.
That's okay. That's all right. That's okay. So I have a good news for you. You're both wrong. Right? There is no difference between these two. They're exactly the same thing. We just fooled ourselves by drawing a
Yeah, I
Lewis
was gonna say that.
you know, by drawing a Lewis structure as such that we think they are different, but in reality, don't know they're not, because they are both tetrahedral, right? Which they have what? 2 groups. These bonding we know is non-polar, so therefore these groups, you know, cause the molecule to be polar. So how do we determine the polarity? There is one way to look at the polarity, look at the vector model. The vector model is very simple, all right? If you have this here, and there are 2 bonded, you can imagine you have a person at the middle and 2 persons to a side exactly opposite from each other with the 180 degree, and from the same strength, they pull in this guy here. So where these guys go, if there is the same strength, what happened? This guy will not go anywhere. So this is what we call it non-polar case. Because if you represent with the vector model, you say this going here, let's say this is more electronegativity here, and this is here. These vector exactly the same, therefore cancel each other out. This leaves what? 0 here, right? No dipole. No dipole, then this is non-polar. Now, what happened is in the same vector model, right? If I just show you the difference, if something with the higher electronegativity, then therefore you expect this pull would be much stronger, right? Then in that case, the vector model would be this side, because you take this one, subtract that one, this is what you end up getting there, right? This is the addition, subtraction of vector model. Now, if you have something like that, all right, which is what? This is what? Trigonal planar. Remember that? In reality, if you have something trigonal planar, this is pull here, this is pull here, this is pull here. It's like a person is standing here, three corner, three other person pulling this person, all right, with let's say a rope or whatever, same length and same strength. Still, this person not gonna go anywhere. So even in the trigonal planar shape, you can see that this, according to this, right, this would be non-polar. Now, the minute we change one of these with something else, or how about this? How about then we have a lone pair here. Then we say, okay, if we have a lone pair, all right, there is no electronegativity difference. We're only looking at this. If you look at this, in order to find out what is the vector model, is very easy. You put like this. You say this is the net effect. Two person pull in this side, and there is no person to hold it, and this person is going to move forward and to this much. Okay. This is very short. A lesson on vector model. We're going to talk about it more later if you need to, but there is an exercise on the geometry and VSEPR, and you will have that exercise in your lab, and hopefully you will do it by then before the exam time, so you will get used to the concepts. Now you see, for the vector model for a tetrahedral structure, you will have something like that, because these two hydrogen, right, they're non-polar, so you mainly focus this. And if, right, two forces pull in this, then this would be net effect, all right? And it would have dipole. All right, so when you get electron move this, well, this would be partial negative and this would be partial positive. The molecule become polar in a sense. So in order for you to find out whether the molecule is polar, you have to draw the Lewis structure, determine the molecular geometry or the shape, determine whether the bond in the molecule are polar, all right? And at the end, you're looking at these bonds, you know, and determine there is a symmetry. Usually symmetrical position cause the molecules to be what? Non-polar. And what I mean by symmetrical position, we got to talk about this later on, okay? These are the polar molecules. You see why they are polar and why they are non-polar, right? Look at them. Look at them carefully, see if it makes sense to them. All right. So this is a chlorine. This is a parent molecule. All the parent molecule, parent structure, like what? Linear. We're talking about both electron geometry and shape to be linear. Trigonal planar, both electron geometry and shape be trigonal planar. Both they are what? These are all tetrahedral, trigonal bipyramidal, octahedral, all of them, they're non-polar. So they only become non-polar when they have a lone pair. And that lone pair, if it is, you have more than one lone pair in symmetry, it's symmetrical lone pair, then that makes it to be non-polar. All right, let me show you what I meant. I think is, well, to get into that, we need to have a little bit of VSEPR. Let's go to VSEPR exercise. Because I have it in the lab, you have this, so you can relate to that. When the lab time come, I'll talk about it again, this one. All right. You see, these are the models we have. The very first, this is in your lab. This here is what? 2 electron groups, 3 electron groups, right? 4 electron groups, 5, and its derivative. Now, if you look at down, first of all, these here, they're all going to be one non-polar because everything cancel each other out. So the only time that you have polar molecule when you have lone pair, but that lone pair shouldn't be in symmetry. So what does that mean? This lone pair is not the symmetry, so it's non-polar. Polar, sorry. This is not symmetry. Polar, 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 polar. Do you see symmetry here?
No.
You don't see the symmetry? How the lone pair located symmetry? So there is only 2 pool here, this and that. They cancel each other out. That become non-polar. Do you see what I'm saying?
No,
Yeah.
I didn't see it. Can you say it again?
Yeah. You see, this atom is like this. A here. All right, is linear. You see that? You have 3 lone pair there. You don't look at the lone pair when you look at the what? Polarity. So if there are 2 people up and down here, pulling this person at the center, he will not go anywhere. This is non-polar.
Got it. Okay.
Yeah.
Yeah.
Now, in this case, this is polar. Why is it polar? Even though these 4 cancel each other out, this one here, there is nothing to cancel it out. In this one, this is non-polar because there is a symmetry in lone pair position.
Okay, it makes sense.
Yeah. This one again is what? This is polar because you have a bonded atom right there somewhere here.
Right.
This one again is
Non-polar.
non-polar. You see that?
Okay.
Predict whether NH3 is polar or non-polar. That should be very easy for you, yes? All right, let's see. Yeah, that's true. We do the Lewis structure. And then from Lewis structure, obviously the electronegativity difference is polar bond, right? Therefore, this molecule would be what? Polar. With everything going toward the nitrogen, so net effect would be what? Upward right there. This would be the negative. It should be drawn here actually. That's how it's gonna go. Okay. All right, decide whether the following molecules are polar or non-polar. This one is fun. Can you do this one?
Let's do it.
Let's do it. I already done a Lewis structure, so this for them shouldn't be difficult. So looking at this one, you can see here why this one is what? Polar. And the other one, you're looking at it as trigonal planar. And what do you think? This would be what? Polar bond, but symmetrical shape, and that makes it to be non-polar. Okay. All right. We got the overlap in hybridization. I think I'm going to work on the hybridization. Why hybridization? Why are we doing a hybridization? What happened, you know, we went over the electron configurations. We learned quantum number, electron configuration. We learned Lewis structure. We learned VSEPR. Now we're doing hybridization. What is exactly we're seeking to find out about hybridization? Now we are looking at the bonding, and we're looking at the covalent bonding. Of course, Lewis structure suggests, you know, how the electron arrangement is. From VSEPR, we get the polarity and geometry. but it's still, we're not clear exactly how this bonding takes place. Let's look, the easy an example would be this one. I mean to do green, but that's okay. CH4. Now, if we do CH4, all right, let's see what can we do for carbon at the center. I'm not going to waste time doing the Lewis-Dot structure the usual way. Just do it quickly here. This is what we get. That's you get from the Lewis-Dot structure. And you see, as far as what you see here, you understand the carbon. What's a carbon valence electron, folks? Anybody know?
4.
4, very good. So if we were right to the electron configuration of carbon, what is the electron configuration? Carbon would be what? 1s2.
2s2.
Uh-huh. And 2p what?
2p2.
2p2. And that's the 4 here, right? That's the one we are concerned with. Why? Because this is the valence shell, right? Valence electron. Now, if we want to see how the bonding takes place, it should be fairly easy. We can look at what? We look at the what? This right here. All right, let's see what we have. If we look at the way the energy is set up, right? And this is energy. You will see that this, I'm not going to draw a box, just put line here. This stands for what? 2s. And then 1, 2, 3, for p orbital, you should see what? 3 orbitals. Now, this is what you see. Now, I'm just saying that if we look at only carbon electron configuration, that's what you see, right? So you see 1, 2, and then here P, it has 2. Everybody see what I'm doing? Do you agree with what I'm doing? Do you see what I'm doing, right? All right. Now, if this is the case, so how the bonding takes place? You know you have 4 hydrogen, right? Look at here. And each hydrogen is going to bring 1 electron, all right, to be paired with what? Carbon. Because remember, when you look at this, you look at the Lewis-Dot structure of carbon, and then you look at the Lewis structure of hydrogen, right? What do you see? Hydrogen, each one of the hydrogen bring an electron here. Now, do you see that? And you see this bonding here happen. All right, that's very clear right there. They're going to be sharing electron, then they end up getting a bonding. All right, but now here in this picture is not clear, because if you say 4 hydrogen bringing 4 electron here, okay, bring 1 electron here, bring another electron here. You could put 2 here, right? They say, okay, I have a full orbital. That's what happened, because that's what carbon reached the octet. You guys see that? By getting about 4 electron from 4 hydrogen. But this picture, this right here, the picture you're looking at it doesn't make sense. So valence bond theory suggests, it says, okay, look, first of all, you cannot have valence bond theory and hybridization separate. They're all together. Valence bond theory and hybridization is together. Foundation, what's the foundation of valence bond theory? That the orbital overlap to do what? To pair electron. It says, no, this is not going to happen. What is going to happen? All right. This is what's going to happen. It's going to be what? These orbitals, they're going to be hybridized. Hybridized meaning what? They're going to be mixed in such a way. Which orbital are they? You take a S, right? And you take 1, 2, 3p. Remember, this is S, P, P, P. You see it's real, S and P, right? You mix this and make this into what? What we call it? sp3 hybridized orbital. Now, carbon has 4 electrons, right? Look at this, 1, 2, 3, 4. In this regard, you understand this orbital, it has to be promoted up there, and energetically, you see the reason I put this line in between, that means it stay a little bit of above S and a little bit of below P. Because of this mixture, energetically is in between right there. And in this format, so it's very nice because you can see each 4 hydrogen bringing an electron, all right, sharing electron with what? Carbon. And now in this model, the model that I'm showing right now, you see how 4 bonds, they are equal. Whereas in this one, it's not clear what's going on. So to complete the valence bond theory, all right, we hybridize orbital, meaning we mix them together. We mix them energetically and, you know, exactly entirely mechanically, so they can what? Mix with the orbital from what? Which orbital is that? You see, this is the p orbital, and you have s orbital from what? From the hydrogen, right? Now, let me just pause right here. This is very good. All right, very good. This model, we like that. This is a model that we can work with. But let's check one more time exactly what is what valence bond theory and hybridization. Go by definition right there. All right, I wrote that for you so you can see what's a valence bond theory is. And let's look at this like word by word, try to understand it. Now, valence bond theory, right? Valence bond and hybridization is right here. See what it is. Covalent bond is formed by overlapping of 2 half-filled valence atomic orbitals of 2 different atoms. That's how the covalent is formed, right? 2 orbital, which one of them is half full, right? They get filled, they get paired through what? Overlapping and forming a bond. So in this regard, electron in overlapping orbital get paired and confined between 2 nuclei. Now, this is a key point. There are 2 types of what? Covalent bonding. How is that 2 types of covalent bonding? How is that possible? Okay, this is where I'm going to show you. If you look at, for example, S and S, let's talk about the sigma. In sigma, what we call it internuclear access. Real here, see 2, for example. All right, 2s orbital, right? 2s orbital coming together, and remember you have an electron here. You have an electron there coming together for electron to get pair, right? Electron gets pair, and for this, because is direction of internuclear access, we call this head. I love to call this head to head. For this, we call it what? This is sigma, right? It would be S and S. Now, we could have S and P, right? For the S and P, you will have something like that. I'm just giving you different examples so you can see here. These electrons get paired here, right? this would be sigma S and P. All right. Now, also you can have, let's see, P and P, right? You can see that clearly. You can have periodability here. Sorry, it is just. If you look at this, these are all internuclear axes right here. Yeah. You see that? They're all internuclear axes. Alternatively, we can have side to side. There are not that many options for side to side. You can have a side to side. All right. And I show you how is possible to have side to side and, head to head. If it is a side to side, this kind of pairing, we call them what? Pi. You got what I'm saying? So you see, you have a various type of the sigma, but for pi, you have what? One thing. So obviously, sigma is much strongest because internuclear axis, and pi is a little bit weaker than sigma. So great, but how this happens? How this type of bonding, because now we're talking about the bonding, right? Two types, sigma and pi. How that happens? Okay, I'm going to show you here how that happens. Let's imagine, let's just a couple of things you understand. If I have a carbon-carbon bond, this can have only sigma bond. If I have a carbon double bond, this can have sigma and also pi bond. If I have a carbon-carbon triple bond, then I have two of them is pi. It doesn't matter which one we assign, and one would be sigma. Now, if I show the carbon-carbon triple bond, then you will see what is a single, double bond, all of them, you can see that. Look at here, two carbon. Yeah? Two carbon, I just don't take carbon out so you can see this clearly. First, we look at sigma bond. These are internuclear axes. Then you can see what? Side to side for this one. Remember, this is a p orbital, right? A p orbital made of how many orbital, folks? How many orbital?
3.
3 orbitals. And this is the third one. Deliberately, I make it like that, so you guys can see these are actually X and Y and Z, but I can show it to you like that. Now, the bond here, this is obviously internuclear axis. This is sigma. The bond here, look at this. This is a pi. And the bond here also is what? Pi. So when I say, if I have a single bond, this is a bond here. You have a double bond, you have another one, which is a pi. Now, if you have a triple bond, you have another one, which is also the pi. You got what I'm saying? So this would be sigma, this would be pi, and this would be pi. This is with every time you have a single, double, triple bond. Same thing with nitrogen. Okay? All right. Now, one thing about the hybridization, if you recall, all right, if you recall, when we were doing a hybridization, we pointed out to you that as far as the hybridization goes, all right, you have to have you have to have an understanding as far as the hybridization scheme goes. What does that mean? That means basically, I don't know if you guys were paying attention. I don't want to bring the whole things up and just put it there, but I just briefly go over it here. Make sure you guys have a good understanding of what I'm saying. If you have two electron groups, right, then you should have sp hybridization, right? And this is the sp hybridization 180 degree. This is two loop right here. If you have three electron group, what kind of hybridization you guys going to have? sp2. Do you guys understand what I'm saying? Look, this is not too difficult. Two group, S and P. Three group, you have what? spp. You guys see that, right? So if I put four groups, what do I get here, guys? Help me with that.
SP3.
Very good. sp3. If I have five group, what do I get? Remember, p is only 3 orbital. You have to go to the next would be what? Next would be what?
D.
Yes, sp3d. You see that? And sixth group would be what?
SP3D or 2. SP3D2.
Right? Let's talk about the hybridization. How do we do really hybridization? Guys, there are one thing is very essential in hybridization. Now, this is absolutely essential. You only can hybridize, all right? You only can hybridize this is the only thing you can hybridize. You can hybridize only what? Pay attention here. So we don't have this problem. Sigma overlapping and LP. LP stand for what? Lone pair. Huh? Sigma and lone pair. Because every time you look at the Lewis-Dot structure, folks, all right? Every time you see the Lewis-Dot structure, you should be able to tell me, all right, whether you have sigma, pi, and lone pair. Can you tell me that when you look at the Lewis-Dot structure? Is it the information you can get out of Lewis-Dot structure? Yes or no? Because when we do the Lewis-Dot structure, we find the electron arrangement. Electron arrangement tells us we have single bond, double bond, and what? Lone pair. We have a single bond, double bond, lone pair. Not to say all the double bond, they are pi, but at least we know one of them is sigma, the rest is going to be pi. So let's start from very beginning, something small. BlCl2. When you do this, right, you want to write the, you want to do the hybridization for this. I'm not gonna start doing a Lewis-Dot structure because you probably by now you should be able to do that yourself. I do it quickly here. Yeah. That's what you get, right? Now, as I said, try to figure out what's going on with beryllium. Beryllium, all right, what is the hybridization of this? To do the alone hybridization, just look at the hybridization. We say, okay, we look at the electron groups. How many electron groups you see for beryllium? It is clear you have two electron groups, right? You see, hybridization is scheme. You think it's difficult, but it's not. Is exactly like a VSEPR, right? Electron geometry, isn't it? So the minute you find out you have two electron groups, you know what hybridization you're going to have. Two electron group, what hybridization, folks? This is 2, 2, sp hybridization. For the under the sp hybridization, how many sigma bond you have? You say 1, 2, right? You see clearly 2. How many pi you have? 0. How many lone pair you have? 0. So you want to do the hybridization? You do the electron configuration of what? Beryllium. Electron configuration of beryllium is 1s2, 2s2. In that regard, all right, you have here energy, and you have what? S orbital, all right? And when you have this S orbital, I put all the orbitals so you can see that here. I actually put, this one is 1s, this is 2s, and this is 2p. You guys paying attention? P. All right. Now, what is happening with this one? Your electron is here, right? But you only need valence electron. I put this deliberately so you can see we don't need to have what? One S written here. It won't do us any good. We have 2 electrons here. We only deal with what? Valence electron. So if we do valence electron, just forget about even talking about what? Talking about core electron. Just go to what? Valence electron. And here you have 2 electrons. And this is a 2s, and this is 2p, right? I put this here because I have a sp hybridized orbital. You understand that? I am suggesting we take one of the s. All right, now look here. We take the s, put the s here, and we take what? One of the p here, and mix this orbital to form what? sp hybridized orbital. Right? So in that regard, you have 1, 2 orbital left unhybridized. Do we need to worry about it? No, it's just left unhybridized. Now, these 2 electrons, they no longer in s orbital. One of them comes here, the other one goes there. These represent now sigma bonding, because the chlorine will come. You have a chlorine here, you have a chlorine here. Each one bring an electron to get paired here to form what? Sigma bond. You see, I represented the hybridization perfectly in this case. Do you have any question? For those of you who think this is hard, it's not hard. If you pay attention, all right, I will go over it. I like to do another quick, sp hybridized orbital, because so you have better understanding of what we're doing here. Let's look at this compound. And as I said, I want to do another sp orbital. It's a little bit different, so it gives you different perspective. Look at this one is quickly here, C2H2, right? When you look at the C2H2, all right, what's the first thing you want to do? You want to draw the Lewis-Dot structure. To do the Lewis-Dot structure is fairly easy. This is S2. You have to put here, this is what you get. Agree? Yeah? Now you see, looking at this, you can say what kind of hybridization is that. Somebody say hybridization, you guys say hybridization for what? You want to do the hybridization? Great. Hybridization for right. Please specify the atom you want to hybridize. Okay, I want to do it for this carbon. I say, you want to do it for this carbon. So for this carbon here, the hybridization would be what? Guys, how many electron group around carbon? Please talk to me.
2.
2 electron group. Remember, triple bond count as how many electron groups? 1, and single bond count as 1. So 2 electron group. Therefore, the hybridization would be what?
SP.
You see, we're still looking at sp hybridization. It's so easy to see that, right? So here we have what? Sp hybridization. That's not a problem. Sp hybridization. All right. Now I'm asking you in that regard, let's see. This is sp hybridization. We want to know how many sigma bond you have, guys.
2.
Yes, 1 here, and one of these has to be 2. How many pi 1 you have?
2.
2. How many lone pair you have?
0.
0.
0. All right. Now, if you do the carbon electron configuration, I'm doing it quickly here. 1s2, 2s2, 2p what? 2p2. So you do the S and P right here. Yeah. And remember, we're just dealing with this, not with the core electron. So you have 2 electrons here and you have 2 here. Now, what we are saying, this is a sp hybridization. So S and P hybridize here. This sp hybridize. All right. And the rest is going to be how many? 1, 2p orbital left unhybridized. Everybody see that? Now, carbon has how many electrons do you see here, folks? Four electrons. So if this is 4 electrons, would be 1, 2, 3, 4. Remember, we are saying one of this is sigma, 2 of this is pi. And if you recall, what did we say about sigma and pi? We just said about sigma and pi that sigma, it is part of hybridization, but pi is not. You guys with me? Pi is not part of hybridization. That is why this is a sp hybridized orbital right here, all right? And it only consists of sigma. Now, in this picture that we are presenting is perfect because these pi, these 2 here, is going to be get paired with another carbon, this carbon. This carbon is going to come, all right, make, all right, 1, what, pairing here, and this hydrogen is going to come, make another pairing here, make this sigma, and for the other carbon also going to get paired here 2 other electrons, all right, to make this one to have a full paired orbital. Okay, and that is the sp hybridized orbital. I don't have to explain everything I did. I'm just doing it for you so you understand exactly step by step what's happening here. Do you have any question? Let's look at another one, sp2, sp2, right? Look at this one, BCl3. I'm doing this quickly so you will see. Guys, you gotta do the Lewis-Sutter structure yourself, and by now I am assuming you guys are perfect in that sense. Right, this is boron, it has 3 bonds here. Now, electron configuration is what? 1s2, 2s2, 2p1, all right? Now, what kind of hybridization we have here? Can you look at the electron group and tell me what kind of hybridization you have, please? This is not so difficult. How many electron group you have?
2.
Yes.
3.
Guys, you count the electron, right? These bounds is our electron. So how many you have? You have 3. So if it is 3, it is spp. So we call this what? sp2. Somebody said it, right? All right. So now what do we see here? How many sigma bond we have?
3.
3. How many pi you see?
0.
0. Do you see any double bond?
No.
Now, how many lone pair you have? Don't say 2 because you don't see any lone pair on
1.
boron. 0, guys, 0. You got what I'm saying? Unless you have done a wrong Lewis-Sutter structure, all right, then you should say whatever many you have done. But if you came up with this Lewis-Sutter structure, you have 0 lone pair on boron. You guys see what I'm saying, right? Okay. Now we're suggesting we have sp2 hybridization. This is very easy. S 1, 2, 3, and this is here, 2 electron here, 1 electron there. You hybridize it to spp, and one of them left hybridized. Now, how many electrons you have? 1, 2, 3. 1, 2, 3. Perfect. And you have nothing there. So nothing to worry about, because as you see, chlorine would come, 3 chlorine will come here, bring electron here and pair them. And this is a perfect picture. All right, I'm gonna do a, no, I wanted to do more, but that's okay. We're getting out of it. We already done the sp3 hybridized orbital of methane. You remember that? I just did that. CH4, that would be sp3. I want to do another type of sp3. All right, this time I want to do this. Right? All of you should know how to do the Lewis study structure for this one. How many electron groups? Huh? Everybody see is 4 electron groups. So therefore, what's the hybridization? Somebody.
sp3.
sp3, because it's 4, guys. Look, 1, 2, 3, 4. So this become what? sp3 hybridization. Now look at it. How many sigma bond you have?
3 sigma bond.
How many pi bond you have?
0
0. And how many lone pair you have?
1
1. Now you see, you never dealt with lone pair, but this is going to be easy. Very easy. For ammonia, if you do the electron configuration, is 1s2, I mean for nitrogen, 2s2, and 2p what? 2p what? 3. Yeah? So this means we're going to be interested in valence. All right, so we're going to do 1, 2, 3, and 2 here. And 3, 1, 2, 3 here. Yes, we hybridize in sp3. That means we're taking everything and hybridize that. Then it's going to get a what? We're going to get a 1, 1 for S and 3p here, right? This is sp3 hybridization. S and okay, I put the S to S, 2p. I do it a little bit fast here, right? Now you see, folks. Whenever you see you have a lone pair meaning what? You have how many electrons? 2. If you have 2 electrons, right? Go ahead, put the lone pair here. If I put the lone pair there, how many electrons I'm left? 1, 2, 3. Then you have 1, 2, 3. And these 3 comes from 3 hydrogen here, form a sigma bond. Do you guys see what's going on with that, huh? Let's do another one. We do water, right? You do water, you know what's the electron configuration of the water for oxygen? Anybody? 1s2, 2s2. Handwriting getting worse. And 2p what? 4. And the water, you're going to have this. So how many electron groups?
4
4 electron groups. So that makes the hybridization to be what?
sp3.
sp3. How many sigma bond?
2.
Yes, 2. How
2.
many pi bond?
0.
0
How many lone pair?
2.
2
Very good. So here we go. I do S, 2s, and 1, 2, 3. Here, 2 electron. Here, 4. 1, 2, 3, 4. Right? And then I hybridize them, sp3, everything gonna be there, right? This is hybridized orbital. Now you're going to have 2 lone pair. Do the lone pair quickly, 1 and 2 lone pair. And that leaves you 2 electrons. This 2 electrons is already gone, 2 electron, 1, 2, to make what? Hydrogen comes, make a sigma bond here. You see that? Such a beautiful picture, isn't it? Huh? Everything is falling in place right now. There is no more confusion here. You know exactly what's going on. Let's do, let me, each wanted to do something a little bit sp3d, huh? Is that what you want to do?
Yes.
Yeah. I'm not going to do a lot, because if I keep doing a lot, meaning I'm going to be doing what? All your assignment for you. What I want you to do is, guys, you know, try to finish hybridization. And for those of you who have class with me on Wednesday, right? Come to see me on Wednesday. And those of you who have class with me today, come see me today. I will do it for you. Or you all gonna come Wednesday. Welcome to come Wednesday class, because hybridization is gonna be part of your class. Oh, let's do one quick one. PCl5. If I do write that here, you know Lewis dot structure is what? Is like this. It has to be like that. You see, folks? I'm not going to put the electron there for you. So you will see how many electron groups you're going to have here. How many electron groups?
5.
Yeah. This is going to be sp3. This is 4. And have to with 1d is going to be 5. And how many sigma you're going to have?
5.
5. And how many pi? 0.
0.
And how many lone pair?
0.
0. So this is going to be fairly easy. If I want to do the electron configuration, this would be, I just put the valence shell, 3s2 and 3p3. We did, because this is like a neons, okay? I do shorthand right there. Now, if you look at that, you know, for this electron configuration, so you put the S here, and then you have 1, 2, 3 P, right? And this is 2 electron. This is 1, 2, 3. Now, obviously, you have to hybridize. Remember, when you hybridize in a d orbital, it has to be empty orbital. You cannot go to the core and get the electron that get the orbital that is full of electron. So 3D in this regard is what? Empty right there. 1, 2, 3, 4, 5. So when you hybridize this together. You take this S from here. You take 3p, 1, 2, 3, and then you grab one of the d orbital, you put it here. So this way you have 1, 2, 3, 4, 5 electron. 5 electron goes here, right? As you know, this has to be S, P, 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 D. So this is, you call it sp3d hybridized. And those the other orbital left unhybridized. Did I answer your question? Huh? Now you see why I paused and I went over the lecture slide, went over the whiteboard, because your textbook doesn't do a good job in explaining hybridization, in my opinion. That's what I think. If you are interested how the sigma and pi and so forth is formed, you clearly see here, these are physically showing you how pi, how the sigma bond is formed between 2p orbital here, all right? And between S and P, and this is between 2S. Now, it's terms of energy showing you here. Now, hybrid orbital, the way you put it in all one same energy level, I don't like it. I like the way I was doing it. So I show you the S and P, and I show you the core electron. They're not involved. So doing it like that, I don't like it. It's a little bit confusing. but end of the day, they get the same thing in terms of hybridization. Now, your question is, we have a sp hybridized orbital. We're suggesting that there are two electron groups. So when they mix, when they physically, mechanically, S and P mix, they create this shape. And you have two of them like that. Then become what? Linear. You see this is still in here, and this one is here. All right, but you cannot see. They're not showing you, but they're mixed in orbital like that. Now you see a sp in case of beryllium. You look at hybridized orbital in terms of what? Trigonal planar. How it's happening? You have one s orbital, one p orbital, one p orbital. You see, this is different orientation. That's why you get this mixture of three right here. And then when they come together, they make what? Trigonal planar. So also same thing for sp3 hybridized orbital. You see sp3 hybridized orbital, you have one s and 3p, they're getting mixed. So you get this mixture and they all put together, they become what? The tetrahedron. Now, I mentioned that lone pair is a part of the hybridization. You see the lone pair is part of hybridization, and the sigma bond also part of hybridization. But the pi is never part of hybridization. Now, in terms of hybridization scheme, we already went through all this, you know. Okay, and I show you carbon can have different hybridization. Higher order hybridization, sp3d, that's another example. All right. Yes. Now here again, another sp3d hybridized orbital showing you how the d comes from what? Empty d orbital. Okay. sp3d2. Right, now you take in two of the d orbitals. They are empty d orbital, by the way. Okay. Now this hybridization scheme, earlier I went through it. Now if you were predict the hybridization on different atoms like this one, all right, what do? What's the first thing you do? You have to draw Lewis dot structure. All right. You don't need to do the things we did as far as the electron goes, because you can look at each individual and see how many electron group you have. You can find the hybridization. What's the hybridization on this one, folks? This oxygen.
sp2.
sp what?
sp3.
You see how many electron groups?
You said
yes. On this oxygen, same. In this oxygen, same. What about this one?
3.
What do you mean? What's a hybridization?
Oh, sorry. sp2.
There you go. Okay. Okay. Any question? All right. What about this one? You also need to do what? The other Lewis structure. All right. And that's the Lewis structure you need to come up with. And look at the oxygen. What's the hybridization of oxygen? Okay. How many electron groups for this oxygen?
3.
3 electron groups. Everybody agree on this, right?
Yeah.
Yes.
Yes.
How many electron on this one?
3.
3 or 4?
3
All right. How many electron group in this one?
is 4.
Do you guys see 3 S P P? 3 S P P. 4 S P P P. So what's the hybridization for this? Is sp2. What's for this one is sp2. What's for this one is sp3. Do you guys see what I'm doing or no?
Yes.
Right? To know the electron groups, you should know the what hybridization. All right. And these are showing how these sigma bond and the pi bond is formed. Right? So the different sigma bonds, sigma is internuclear axis, right? And the pi bond, what side to side. You look at this one, this is always sigma. This one sigma, 1 pi, this one sigma, 2 pi's. Now it's showing you the molecule here. How is it overlap, right? Physically showing you what the overlap will look like. So you can see that. You can see, for example, sigma here, and also this is the pi right there, right? I just draw it like that so you see that this is a pi. And you see you have double bond here. One of them has to be sigma, the other one has to be pi. And this is showing a triple bond. Obviously in triple bond, you have what 1 sigma and 2 other has to be pi, and showing you here the sigma and pi's, you know, how they are formed. They are kind of on top of each other, so it's hard to see. All right. Now, one thing is important to understand that whenever you have a double bond, there is a restricted rotation because single bond, the molecule is dynamic. It can have a free rotation and move around. All right. And that's the important property, by the way. To have a double bond, the double bond will make it rigid and it cannot move, whereas single bond, they can rotate around the axis. Now, the localized electrons, we talk about the concept of the delocalization in terms of one of the double bond moving around, you know, forming different resonance structure, and this give you equivalent resonance structure, right? So delocalized electron is just the electron go over all over the molecule, right? And you see in case of benzene, you have that because you have a double bond, all right? And it gives you resonance. All right. So valence bond theory, you should be able to use the concept of hybridization to rationalize the structure predicted by Vesper, which we could do that. You should be able to tell what type, give the name, and how many orbital present in hybridized orbital. You should be able to do that. So this is a problem with valence bond theory. What's the problem here? In the valence bond theory, when we look at things, you know, there are certain properties we cannot find out those properties. One of the property is what magnetic property of oxygen. For that property, just using what we learned from from valence bond theory and hybridization, we cannot predict what's going on. Let's look at the oxygen. If I do the Lewis dot structure and do the energy for oxygen, this is what I come up with. You guys see that? This is what I come up with. That's correct, right? You know, you have a sp, right? All the orbitals right there. And then you start to hybridize in them. And you put an electron there and see what is happening here. It's going to be a problem. Yeah. Maybe I just show that to you a little bit of easier in that sense so you can understand. This is O2, right? When I draw Lewis dot structure, what do you see here, folks? What's the hybridization of oxygen? Folks, 3 electron groups, that gives us what? sp2 hybridization. How many sigma bond?
1,
How many pi?
1,
How many lone pair?
2,
2, very good. So in doing the hybridization, I want you to pay attention. I am only focusing to 2s2 and 2p4 on oxygen right here. I do the hybridization of oxygen. So therefore I have electron here, 2, right? And then 1, 2, 3. You have 1, 2, 3, 4. You guys see that? Is that okay? Now, when I hybridize, what's going to happen? It would be sp2 hybridization. That means 1s come here, 2p, and is left 1p unhybridized. You have 2 lone pair. I'll put 2 lone pair here. These 2, right? Lone pair comes here. Very good. You have 2 lone pair, right? You see that on oxygen. And then you have one of these sigma and the other one pi. All right? That's very good. That's very good. Now, another oxygen, which is this oxygen, bring the electron down here to pair here and bring another one here to pair here. Do you guys see what I just did? Now you hybridize to get everything paired. Remember, that's the beginning of the definition of valence bond theory. And the reason now I'm emphasizing on this part, this particular part, is because I want to tell you what is the problem with our model. The problem with our model is our model at the end of the day is suggesting all the electron they got paired in case of what? Oxygen. Am I right or wrong? All the electrons getting paired. If that is going to happen, then everything get paired. We would say oxygen is diamagnetic. You got what I'm saying? We say oxygen is diamagnetic. However, experiment shows that oxygen is what? Paramagnetic. That's why we have problem with this model. This is exactly what we have here, right? You see, you have for each one of the oxygen, when it's hybridizing, you still going to have what, electron get paired there. And if electron get paired, right, it doesn't matter S and P, here we're talking about all the electron getting paired. Basically, for each oxygen, you're going to have what? If you write the electron configuration 2s2, 2p4, right? For this, you have total of how many electrons? 6 electrons. So of 6 electrons, 2 of them goes what? 2 lone pair goes here, right? You see that? And 1 goes to what? Sigma bond, and the other one goes to pi. The sigma and pi, they left unpaired. Yes? And you pair them with this other oxygen. You got what I'm saying?
Mm-hmm.
So ask me a question. If you have left electron unpaired, all right, because you have 4 electron here basically. So in the 2s electron, you have this, and in the rest, you have 1, 2, 3, 4. And in a hybridized model, you have to pair the other 2 electrons, and you pair them from the other oxygens. Okay? Valence bond theory, its problem is it does not predict what the paramagnetic property of oxygen. All right. Now, one note on valence bond theory, on MO theory. MO theory, all right, is basically the principle of looking at how the electron interact with the other in terms of wave. Because when we have wave, right, we look at the wave, we can have 2 types of, interaction as far as the wave goes. Do you guys remember those types? One is considered to be what? Constructive. The other one would be what? destructive. So whenever two-wave MO theory, all right, two-wave interact with each other, we expect to be one of them forming what we call it the bonding, all right? The other one is anti-bonding. So every time you look at some bonding, all right, you can consider there is a possibility of anti-bonding. Now, since s orbital, you can only form one, all right, one type of bonding compared to, for example, p orbital. Remember, we show p orbital, you can have sigma, you can have what? 2 pi, right? So for each one of the bonding, you can have what? Pi bonding, all right? Which means, what it means is exactly, if 2s orbital from the hydrogen come together, there are two possibilities. They can either form a bond or they can bond non-bonding. They can either make sigma or sigma star. Remember, these are two possibilities. Like the light switch, when you go to the light switch, there is two positions. One is on, the other one is off, all right? And MO theory works on the same principle because in looking at two-way, right? If these are all in phase, they are in phase, they form what we call it bonding. This is sigma. If they are not in phase, they're out of phase, this create what we call it anti-bonding. That is sigma star. So we look at the orbital like wave, all right? We consider for any on switch, for any bonding is Y anti-bonding. So we apply the same principle every time, all right, we have a bonding. For the s orbital, there is only one possibility. You can have what? Sigma or sigma star. Now you look at the p orbital. For p orbital, then what's going to happen? When you look at the p orbital, what do you see, guys? You should see, right, 1 sigma, and you can see 2 pi here, right? Remember, is 1, 2, 3. And one of these form what? Sigma bonding, and the other two forming what? Pi bonding. Okay? That's the principle of MO theory. Now you want to find out, when you do the MO diagram, you want to find out bond order. All you have to do, take the bonding electrons minus anti-bonding divided by 2. That gives you what? The bond order. Let's look at this. This is 2 hydrogen here, right? When 2 hydrogen come together, you have 1 electron here, 1 electron there. Obviously, both electron goes to the lowest energy, which is what? Bonding. Remember, this is a sigma 1s. This is a sigma 1s star. You guys see that? All right. Now, if you look at the same thing here, as far as the bond order, you say bond order is number of electron in what? In a bonding orbitals minus number of electron in anti-bond. So 2 minus 0, because there is 0 here, and that would be 1. That gives you bond order of 1 for what? H2, for hydrogen. Now, how about the case that we have helium-2? Helium-2 doesn't exist. You guys know that it doesn't exist, but we are doing this as a trial to see how everything works, because you have total of what? 4 electrons now. 2 of them has to go what? To sigma, and the other 2, they has to go to anti-bonding. So if it goes to the anti-bonding, you calculate the bond order. In this case, the bond order would be 0, that which indicate that this one does not exist for helium. All right. Now, in terms of the higher level, arrangement, such as when we go, for example, lithium If we go to beryllium, these are all, you know, it's fairly easy. When we go to the boron, carbon, nitrogen, oxygen, fluorine, neon, all right, you have involved p orbitals. Now to represent p orbitals here, all right, remember p made of 1, 2, 3, 1, 2, 3 here, right? These p orbitals, they make one of them form a sigma, and obviously one has to be sigma star. The other one making 2 pi, all right, and you're obviously going to have what? For any on switch, you're going to have off switch. For any sigma, you have to have sigma star. For any pi, you have to have what? Pi star. Now you see, look at this arrangement. This arrangement that you see, not all of them have the same arrangement, and I get into that in a second. All right. There is going to be a switch, and what happened from boron, carbon, nitrogen. Let me just put them here. I will show you this again. Boron, carbon, nitrogen. You have one arrangement, and from oxygen, fluorine, neon, you have another arrangement. These three and these three is different, and the only difference is these, they switch places, all right, and switch places in a way that sigma comes down and a pi goes up, all right? All right, I can show it to you here better. In typical scenario like oxygen, right, you would have sigma S, sigma star, all right? And then you have for 2p sigma, right? And then you have pi sigma. Now you're looking at the left side, what is happening? These are switching, these coming down, this going up, all right? And I just mentioned the reason that it's got because of the interaction, S and P interaction, they call repulsion, and that switches. For you, all right, for you, the easiest way to look at it is boron, carbon, nitrogen, they have their pi is below what? Sigma. For the oxygen, fluorine, neon, the sigma is below pi. Okay. Now let's do one quickly, see how you can do this. All right. Draw the molecular orbital diagram of N2 minus. Remember, we are trying to use molecular orbital. So if you do the molecular orbital, you should know what the atomic orbital look like. When you have an atomic orbital, all right, and the pattern in this case, remember, pi is coming below sigma 2 pi. This goes where this switch you have here. Now you do the electron configuration and Lewis dot structure of all of them. You can see clearly that nitrogen is going to have what? Nitrogen is going to have, how many electrons, guys? Nitrogen has? Yeah. How many electrons?
11.
Yes. It would have what? 10, but it has a -1 that makes it 11. So have 11 because of the charge right there. You have 11 electron. You start putting electron right there. You see, you're going from the top, you go on, all right? And you always put the one that goes up, right? Spin up, and then spin down. Now you look at this, is this paramagnetic or diamagnetic? Since it has unpaired electron, it's paramagnetic, right? Can you calculate the bond order for this? Guys, can you calculate the bond order? Bond order, right? Bond order is equal to what? Bonding electron. How many bonding electron do you see? This is a bonding electron, is sigma. This is a bonding electron, this is a bonding electron. So the one they don't have stars, they're bonding electron. And how many do you see, guys?
3.
Huh?
3.
No, but how many electron we can see? No, you have to count the electron, right?
6.
Yes. And how many anti-bonding do you see? This has a star. This has a
3.
star. You guys see that? So when you calculate in a bond order, you got to make sure that you have to put this in there, you know. Let me see. Yeah. So you get 2.5, right? Is that what you got there?
Wait, how did we get 8 for the,
Yeah. We miscounted, right? 1, 2, right? 3. So how many electrons? 1, 2, 3, 4, 5, 6, 7, 8.
mm,
There are 8 electrons. And as far as the one that is this one and this one. So if somebody asks you to write the electron configuration of that, you should be able to write the electron configuration for this one as well too. Molecular configuration. So this is would be what you could write this sigma 2s, right? You see what I'm doing here? 2 electron here. For this one would be what? Sigma star 2s. How many electron? 2 electron. And this one would be what?
P.
Pi 2p. How many electron?
4.
Yeah. Oh, sorry. 4 electrons. And this one would be what? Sigma 2p. How many electron? 2. And this one would be what? Pi star 2p. How many electron? 1 electron. This is right in an electron configuration for that molecule. Okay. Because I will ask you something like that. All right. Now the valence bond theory, now when you do for oxygen, now everything makes sense. Because now look at this, this is for oxygen is done. All right. We do the MO theory for the oxygen, and for doing the oxygen, you find out the bond order is 2 and everything fall places, and you have unpaired electron here, right there. After, because when you say oxygen, how many electron, total electron you have for O2, guys? How many electron you have?
12.
Huh?
12.
12 electron. So you gotta start putting electron, come here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 12, the way it goes electron here indicate this is what? Paramagnetic. Okay. And you can write the electron configuration the same way I wrote it. Because the reason I'm emphasizing on electron configuration, because that's what I'm going to give you on the test. All right. I don't think I'm going to do any heteroatomic. I do those only diatomic basically. So that shouldn't be any difficult. These are the things I need you guys to know about the MO theory, right? All right.